Let us talk about estimation. What is estimation? Estimation is a statistical technique of inferring the population parameter, which is typically fixed and unknown, from the statistical summary of the sample. The population parameter could be mean, proportion, or variance. There are two estimation techniques: point estimation and interval estimation. Point estimation is a single value estimate of the population parameter, and interval estimation, in addition to point estimation, it provides an interval around that point estimate which is likely to cover the population parameter. Let's understand the point estimation and the limitation of it. The statistical technique for a single point estimate of population parameter is called point estimation. This point estimate is a single value which we equate it to the sample expected value or the sample statistic. We get this guarantee or this confidence from the central limit theorem, which states that the mean or the expected value of the sampling distribution of a sample statistic is the best estimate of the corresponding population parameter. Now, the sampling distribution is a theoretical distribution which we never get to see, but we know that the sample statistic is originating from the sampling distribution. Within the sampling distribution, the most likely value or the expected value of the sampling distribution to occur in the sample is the expected value of the sampling distribution because it has the highest probability. That's the reason we equate the sample mean to be the best estimator of the population parameter. In case of proportion, the sample proportion is the best estimator of the population proportion. Now we understand that because of the sampling process, the inherent difference will occur between the true population parameter and the sample statistic. The difference between the actual true population parameter and the estimated population parameter, which is our expected value of the sample, is called the error in the estimate. This error can be bifurcated into two parts: sampling error and sampling bias. The sampling bias can be minimized by using suitable data collection methodology and a robust, strong research design. Actually, sampling bias is a systemic over and underestimation of the parameter. It happens because of the inappropriate data collection methods or the inappropriate measurement scales or non-representative sample because of inappropriate research design. These we can minimize using the established best practices in data collection and research design. The other part of the error in the estimate comes from the sampling error. Now, the sampling error is the inherent error in the sampling process because of the involvement of the randomness in the process. Now we can reduce this sampling error or by increasing the sample size. We can reduce the sampling error to 0 by increasing the sample size to the size of the population. Right? In that case, we don't need to estimate anymore. We have the true population parameter, which is typically practically infeasible. And if we ensure the randomness in the sampling process, we can minimize the sampling error. And finally, if we are still in doubt, we can reduce it by replicating the study again. Now we know that the error in the estimate cannot be brought down to 0 because of the inherent processes of sampling. To overcome the inherent sampling error, instead of trying to guarantee a good point estimate, we specify an interval around the point estimate instead, within which we expect to capture the population parameter with a certain degree of confidence. Now this interval around the point estimate is called as the confidence interval, and the degree of confidence around this estimate, or the degree of confidence associated with this estimate, is called as confidence level. We will get into the formal definition of confidence interval and confidence level. Before that, we revisit the premises or the underpinning theory of center limit theorem. We know that in real world, we never actually observe the sampling distribution. Yet it is useful to always think of a point estimate as coming from such a hypothetical distribution, because the sampling distribution is always a normal distribution if the sample size is sufficiently large. So there are some preconditions that we test for or we ensure in the sampling, so that we know that the data is originating from the sampling distribution. So sampling distribution helps us characterize and make sense of the point estimates that we do observe in our sample data. So the sample statistic is the most plausible estimate of population parameter. When we build the interval around this point, the interval is guided by the standard error. Why? Because from the center limit theorem, we know that the standard deviation of the sampling distribution is given by sigma by root n, where sigma is the standard deviation of population parameter and n is the sample size. With this understanding that standard error gives us the basis for building the interval around the point estimate, let us build the definition of confidence level and confidence interval. So confidence interval is the range around a point estimate that likely contains the true population parameter, and the width of confidence interval is determined by the desired confidence level. We will quantify the confidence level as the area under the normal curve within the bounds of the confidence interval. To understand it better, let us say we build a confidence interval which is infinite on the either side of the point estimate. We can say with 100% confidence that the true population parameter will exist within this band. But this is practically useless. On the other hand, we can shrink the confidence interval width to 0, but the level of confidence that this is indeed the true population parameter is also 0. So the confidence is low and the estimate is accurate, more precise. When the confidence is high, the estimate is between minus infinity and plus infinity. So between these two extremes, statisticians worldwide have come up with a convention of accepted reportable confidence levels, which is 95%. What it essentially means that there is a 95% chance that the interval contains the true population parameter. Let us take an example. Let us say if you want to travel to some exotic location in the Caribbean islands. Now you want to know how much will it cost you before you actually undertake the travel. If somebody tells you that it's going to cost you $1,000, we know for sure not every travel can be guaranteed at $1,000. There would be a lot of factors which will determine the true cost. What we are interested in is not the estimated cost of $1,000 or knowing the true cost of travel. We are interested how much is the variance that I would experience in this $1,000. If let us say it is plus minus $100, so if someone says, hey, it costs between $900 and $1,100, you may undertake the study, the travel. But if someone tells you that it can cost you anywhere from $100 to $1 million, in that case, the standard deviation is way too high and you may want to think again before you actually undertake the travel. So point estimate is not what we are seeking for. We are seeking for a reasonable, acceptable level of risk of not containing the cost within a certain band. If someone tells you that 99% of chance it will cost you between $900 and $1,100, you will say, okay, all right, 1% will leave it to chance, and 99% with 99% confidence level, you will undertake the travel. But if the same 99% confidence level tells you it would be between $100 and $1 million, you may not want to undertake that travel. Right. So let's see pictorially how it looks like. So it's a point estimate, which is here in the center. We build a equal width interval on the either side, which captures the area under the curve. So this normal curve will have the point estimate here in the center, the most likely value, and the standard error, which is sigma by root 10, gives us the confidence interval, and how large we want the confidence interval will be determined by how high the confidence that we want. Conventionally we use 95%. The complement of the confidence interval is the area under the curve on the either side of this interval, which is 5% split equally into either tail. Now let us apply this to estimating the mean of the population. So using central limit theorem, the point estimate of population mean mu is the sample mean x bar. So we got the point estimate. The standard error is given by sigma by root n. So the interval estimate at 95% confidence level will be point estimate plus minus the width of this confidence interval at 95% confidence level. So we choose the endpoints of this interval such that it captures the 95% of the area in the center. So we multiply by z, which is nothing but your standard deviation scaled by the standard error. So this width is also referred to as the margin of error. So we know that E is equal to z times sigma by root n. So there are these four quantities. If you are given any three of these, you can determine the fourth. So now repurposing this equation, we can arrive at n is equal to z sigma by E whole square. So if we determine that the margin of error should be certain value with a certain confidence level and the given population standard deviation, we can always determine the appropriate sample size. So we can choose the other three quantities to determine the fourth quantity. Similarly, we can apply it to the proportion also. The point estimate of population proportion is sample proportion p hat. The standard error of the sampling distribution of proportion is root of pq by n. So the interval estimate would at 95% or for a given percentage of confidence level is p hat plus minus z times sigma pq by n. And z that corresponds to 95% confidence level is plus minus 1.96. Similarly, we can repurpose the margin of error equation to get the optimal sample size, which is given by z by e whole square times pq. So we can extend this to variance also using the similar principles, but we will stick to mean and proportion.